Construction to Last is a podcast by Saint-Gobain about those who invent and live the future of construction. For this podcast, I wanted to meet a researcher who works on new building materials. This is for me the basis of sustainable building. If we want to reduce CO2 emissions, we have to work with biosourced solutions, which come directly from nature. I talked to Saint-Gobain about it, but they had a different idea in mind. In fact, even though manufacturers are increasingly using organic materials, such as wood or gypsum, the fact is that you still need mortar and concrete. Mortar is a mixture of cement, sand, and other components. Concrete contains cement and sand too, but also aggregates. These materials are therefore extremely strong, and what they are made of can be found locally. As the production of cements emits CO2, manufacturers are now designing and producing what we call low-carbon cements. That's when Saint-Gobain told me about Chryso, a chemical company specializing in admixtures for construction materials. More specifically, Chryso designs products that are added to the composition of cement and concrete to boost their performance and meet the challenges of construction projects. With the danger of global warming, there are now more and more solutions to reduce the environmental footprint of construction materials, and the admixtures play a very important role in the development of low-carbon cements and concrete. I met Mary, a research and development engineer for Chryso, in the large site located in the Loiret, 70 kilometers south of Paris. With its 250 employees, it is one of the main employers in the department.
So in terms of safety regulations, we're going to the R&D area. I don't have a badge for you, so you have to stay with me.
I followed Mary into a large building, a series of corridors and stairs. Then she told me about her career and how she specialized in cement.
I studied chemistry and I liked it. I was quite interested in inorganic chemistry, and the cementitious material is an inorganic material. It's mineral. I found an internship at Chryso by chance, and I liked it. So I stayed in the sector of cementitious materials.
When Mary talks about cementitious materials, she is talking about cement and concrete.
It's true that cementitious materials are very unloved, and for many years, I think they were not considered at all. It's precisely why there is still a lot of research and development that's being done right now, because it's probably been neglected as a science where you just mix water with powder, then it hardens, and everything is fine. And in fact, it's much more complex than that.
It is more complex because admixtures are added to the cement and concrete. These admixtures are composed of components that act in different ways. For example, they can speed up the concrete setup faster.
For example, when you are on a construction site, you have to build different floors for a house. If you put an accelerator in your concrete, it means that you can pour concrete on the second floor, it dries quickly, and you can go on to the next floor. If you don't put an accelerator in, the job may take longer.
Other admixtures can also be used to extend the fluidity of concrete.
For example, if you have to transport concrete, when a concrete mixer truck, the concrete has to remain fluid throughout the journey, from the place where it was made to the site where you want to pour it. So we use polymers or admixtures called plasticizers to maintain the fluidity of the concrete throughout the journey, so that once you arrive at the site, you can still pour it into the mold or onto the surface where you want to pour it.
It sounds simple, but in fact, it's not simple at all. Mary has to design admixtures that modify the properties of concrete, but without degrading it. Concrete is still used to construct buildings and structures. Chryso tests these admixtures in the laboratory. Before taking me on a tour of the labs, Mary gave me safety shoes and goggles. Between the glasses and the helmet, okay? We arrived in a large room where several technicians were manipulating large machines. It was quite humid.
Yes, it's regulated both in temperature and humidity. The labs are fully regulated because depending on humidity, the cement will hydrate more or less. So it's really monitored.
Mary showed me a machine that looked a lot like a stand mixer. This mixer is used to mix materials, water, and admixture.
For example, we prepare mortars with bowls like that. It looks a bit like kitchen bowls. And they are mixing blades. Pretty big blades, though.
Yes.
Like this. Yes.
Oh, yes. It looks like we're going to make a cake with this.
That's right. We have Kenwood-like machines.
We went to the other end of the lab. A woman was handling mortar blocks.
So they're little rectangles, and in fact, afterwards, we break them by crushing them with a press. And the idea is to see after how long they break. It's called the compressive strength. We compress them and see when they break. And that allows us to know if the cement or future concrete will be resistant or not. And as we put admixtures in, the general idea is not to degrade the mechanical performance.
This question of performance arises even more particularly for one type of cement, low-carbon cement. Following new regulations, Mary receives more and more requests from customers who use this type of material. For her, it is a new challenge.
Because it's not at all the same chemical composition as standard cement. And in general, we don't know this chemistry very well. The hydration reactions are not the same. So in fact, we have to review all our admixtures and readjust them according to the low-carbon cement we receive.
Cement is mostly made of clinker. It's made of clay and limestone that are burnt at very high temperatures, which consumes a lot of energy and releases a lot of CO2. The idea with low-carbon cements is to reduce the quantity of clinker and to add other materials instead, which are much more virtuous.
Among other things, we use clays because clays are found everywhere around us. There are many different kinds, and we burn them to get calcined clays, so these cements with calcined clays are more and more used.
Mary also explained to me that an admixture will not behave in the same way on a standard cement as on a cement with clay. This is due to the fact that clay has a multi-layered structure.
The layers are parallel to each other, and when we add admixtures, especially polymers, they tend to get in between these layers. So instead of making the cement more fluid, they get stuck and they are no longer effective.
Chryso's teams are therefore working on admixtures that don't enter the layers of clay and allow the cements to stay fluid.
So we run tests and see which admixtures are working best on this kind of cement according to their structure. And then we have a whole bunch of tests that we can do to evaluate the fluidity of the cement and see if it is more or less fluid.
Chryso conducts laboratory tests to verify the quality of the admixtures. If conclusive, full-scale tests on construction sites are still required. Recently, Chryso solutions were tested for the Grand Paris Express, the project to build new subway lines in Paris.
They use the materials they plan to use on the Grand Paris Express site, and then they pour concrete with our admixtures and check that the properties are good. That's when they call for tenders with all our competitors and Chryso too. So we propose admixtures, they run tests, and then they validate our solution or not.
When the tests are conclusive, the admixtures designed by Chryso are validated. They are then produced on a larger scale to be used on construction sites. But sometimes it doesn't work as planned at all.
It can happen, because especially at a laboratory scale, we work very finely. We weigh very, very precise quantities and manipulate everything with great precision. It's fine chemistry. At the scale of the construction site, we have much less control over the parameters. There can be a small error due to the weighing, and the outside temperature can also play a role, so can rain and all the environmental conditions. So it happens that we had found a solution. We had the impression that it worked very well in the lab, but on a field test, it did not. So in general, we prefer to repeat several field tests to confirm the results, hoping to verify that it does work after all.
If, after all these tests, Mary sees that the admixture does not tick all the boxes in the specifications, she goes for other solutions. The process starts again. They study, they wonder, they test. For her, this research work is very stimulating.
In research and development, what we like to do is look for things. When there's nothing left to look for, it becomes boring. There's an infinite field of things to look for.
Mary has discovered an exciting world. She is helping to reduce the carbon footprint of the construction industry by designing admixtures for more environmentally friendly materials. And it doesn't stop there, since Mary is also looking into the composition of Chryso's admixtures.
We are working on low-carbon cements, but at our level, we formulate admixtures and we also try to reduce our carbon footprint. For example, in our admixtures, which are made with a lot of water, we try to work with recycled water. We also try to find raw materials that are either recyclable or recycled. So on the scale of the admixture, we are also trying to make progress. And it is also a challenge in terms of formulation. These raw materials are a little different, and we have to formulate things that are stable and just as effective as those we had originally.
Mary will soon be even more directly concerned with low-carbon materials. She and her husband have just bought a house in the country a few miles away. It's an old house, so they're going to have to do some major work. And there, for sure, Mary will want to turn to environmentally friendly cements.
When I have to fill holes in my walls and buy things like plaster, mortar, or cement, I'll check them out. And I always explain to people that we have admixtures in our kitchen we can use, because salt, for example, accelerates the process and sugar delays it. So you can use admixtures at home if you want to.
If you want to look at the composition of a cement to know if it is low carbon, Mary has some tips.
The cements are marked CEM1, 2, 3, 4 to know what type of cement it is. If it's CEM1, it shouldn't be low-carbon cement because there's only cement inside. And anything that's marked 2, 3, 4, 5, 6 can be a low-carbon cement. As soon as it contains additions or mineral additions, it's a low-carbon cement because we put less cement or clinker inside.
At the end of that afternoon at Chryso, I wondered if concrete was destined to disappear in favor of other more natural materials like wood. But for Mary, the answer is clear. Concrete will stay because it is locally produced, and also because it is a practical material to use.
Especially because it has very interesting properties, like you can pour it. With wood, you cut the trunk and you have something solid. You have to transport the whole trunk. It's the same for everything that is metal. If you cast a metal beam, once it's dry, it's over. Whereas with concrete, you have much more flexibility. As it is relatively liquid at first, you can transport it, put it in molds with a given shape. Then you just have to reduce the carbon footprint. But I don't think we're going to be able to completely eliminate cement.
Concrete can also be recycled as aggregate to further reduce its carbon footprint. And it's not the only material that can be redeployed on other projects. Almost everything can be reused. Wood, stainless steel, light switches, windows, plasterboards. This is a very important issue because at the end of a project, we often find ourselves with a lot of waste, either surplus materials or elements that were removed during the renovation work. We can't let them go to the dumpster and continue to buy only new materials. That's why contractors have taken up the challenge of reusing construction waste. This is what we will see in the next episode. Construction to Last is a podcast by Saint-Gobain. Animation and writing, Samia Basile. Production and mixing, Martin Commandeur. Coordination, Bartholomew Bell and Kevin Vergobi.